Okay, so last time we talked, we had just focused on switching from simplifying a rational expression. You know, you were given a rational expression and you simplified simply, you just factored the numerators and the denominators, and then you canceled out any common pieces, and then you just shortened it. All right. And then after that, we learn to start multiplying and dividing rational expressions with one another, similar to what you did with fractions way back when. All right. You would multiply across, and then you would add the exponents if you had to do that, or with the division, you would keep the first fraction, you would change division to multiplication, and then you would flip flop or use the reciprocal of the second fraction. All right. Now, on this time, we are going to focus on adding and subtracting rational expressions. Now, just like what we've been talking about, treat it like a fraction. All right. If you treat it like a fraction, it becomes a little bit more simpler. If you treat it like some weird problem, it will get very complicated very fast. All right. Treat it like a fraction. All right. So, the essential question, or actually, we flip flop the essential question and learning targets. All right. The essential question is, how do you add and subtract rational expressions? And then the learning target is what we're going to be focusing on is I can add and subtract rational expressions. All right. If you're able to add, you should be able to subtract. If you can subtract, you can add. Okay. Some of the vocabulary you will hear is lowest or least common denominator. Do not worry about complex fraction. So, to add and subtract rational expressions, all right. So, to add and subtract rational fractions, think of the same rules you would with fractions. All right. And then, however, always simplify first. Simplify if you can. So, first things first. If you get like denominators, meaning this denominator is the same thing as this denominator, all right. When you are dealing with that in fractions, you simply add the numerator to the denominator, or you're in this case, you are going to combine like terms. You're going to combine like terms in the numerator, and you get to carry over the denominator. All right. You're not going to add the denominator. We're not going to add this x to this x and this 3 to this 3. All right. Not what we're going to do. That is our denominator. Just like if it was a 4 or an 8 or a 12. All right. That will be our denominator regardless. For the numerators, you're simply just going to combine like terms. All right. This 3 is going to combine with this -2, which will get a 1. And because x squared is all by itself, it becomes 1 plus x squared. All right, over x plus 3, because x plus 3 was our like denominator. We combine like terms. 3 plus -2 results in 1. And then there is no other x squared, so it ends up being 1 plus x squared. Now, you're probably thinking, well, what happens if we get a unlike denominator? What happens if the denominators are completely different from one another? Well, here's what you're going to do. You're going to find the least common denominator. Most of the time, that's simply multiplying the two denominators together. All right. You're going to take this denominator and you're going to multiply it with that denominator. Okay. So you're going to multiply each rational expression to create denominators. Okay, so our common denominator would actually be this. Okay, that would be our common denominator. So what we've got to do is rewrite it real quick. All right, so we're going to come down here. So 3 over x minus 1 for the denominator, it's going to become x minus 1 times x squared. All right, because we start with x minus 1. Now we're multiplying x squared to it. Now, if you recall with unlike denominators and fractions, okay, say we had 1/4 plus 1/3, we had to get these two to be the same. All right, a common denominator between those two would be 12. To go from 4 to 12, we had to multiply by 3. To go from 3 to 12, we had to multiply by 4. We're going to we're going to do that exact concept, but with variables instead of numbers. Okay. Because we started with x minus 1. Now we're multiplying x squared. All right. Because we're multiplying by x squared, what we do to the bottom, we're going to do to the top. All right, so if we multiplied x squared on the bottom, we're going to multiply x squared on top. So that 3 from earlier right here becomes 3x squared. All right, now we're going to look at x squared and 3 again. Now, we started with 3x squared earlier. All right, so I've got that right now. Now we've got to multiply it by x minus 1 to make it a like denominator like this. All right, and whatever you do to the bottom, you're going to do to the top. Okay. And in this case, you're going to distribute this 3 with everything inside. So that actually becomes 3x minus 3. Okay. So when we go to add everything, our denominator is going to be x squared times x minus 1. We do not have to distribute it at all. He simply gets to stay like that. And then we're just going to combine like terms. And if you recall, when I was back in chapter 4, to combine like terms, I mentioned a strategy. I'm putting different shapes around each individual piece. So triangle, square, circle. All right. I put a triangle around all the x squareds. I put a square around all the x's, and then put a circle around only just the numbers themselves. Because there's one of each piece, we're just going to write from biggest exponent to no exponent. And that is that combined. Okay. So let's take a look at some examples. All right. Going to erase that real quick. Just remember it's rational. Okay. So looking at this. Okay. So 2x squared plus 4x h minus, or all over x2 or x squared h minus negative 2 plus x squared all over x h x. All right. Now, when you first look at this seems totally different than this. However, technically, even though it is written differently, this can be written like this, which is that, and this can be written like this, which is that. So we can say that's the common denominator. All right. It's just written differently. Okay. That's a common denominator. However, it's just written differently. So all we have to do is combine like terms, or in this case, we are going to combine like terms. However, we're going to subtract rather than combining. All right, we're going to find the difference between them. Okay, so using the strategy down here, I'm going to put a triangle around all the biggest exponents, so I know those need to be focused together. I'm going to put a square around anything different outside that, and then a circle outside anything different like that. Okay. So keep in mind, we are subtracting now. We're not combining like terms. All right. We're just subtracting. So instead of combining two, so we're going to focus on the biggest exponent. And in this case, this is 2x squared and x squared because we're subtracting. That's actually going to be 2x squared minus x squared. All right. You're not going to subtract the exponents. You're not going to subtract the x's. You're simply going to take the numbers that are in the front and subtract those. In this case, it becomes x squared. Okay. There's only one 4xh, or there's only one term with xh attached, and that's the 4xh. So we write him next. All right. And there's only one, constant number, which in this case is a -2. Okay. Or a +2 because of that. Okay. Because in reality, this would be keep, flip, change. All right, we're keeping all the signs for that first fraction. We're flipping this to addition, and then we're changing all of these signs. All right, so instead of -2, that's going to be +2. Instead of positive x squared, that's going to be a negative x squared. All right, so our new numerator will be x squared plus 4xh plus 2. All right, and then our common denominator is that, or you can even write that. Okay, either one is acceptable. So that is another example of like denominators, just subtracting in this case. Now let's look at another example of unlike denominators, but we're subtracting those as well. So we have 2 over x plus h minus x minus 2 all over x squared equals something. All right. We know that they are unlike denominators. So the first thing we've got to do is make them like. So what we can do is similar to how we did this. All right. We can multiply this piece over here and then multiply this piece over here. All right. And that will make them like denominators. All right. So x squared times x plus 5. Move it down just a little bit. All right. And then x squared, x plus 5 again. So for this one, we started with x plus 5 for this fraction, but we multiplied x squared. And so what you do, wherever you do the bottom, you're going to do the top. Because we multiplied this by x squared, we're going to multiply this by x squared. So that becomes 2x squared. And because we multiplied this by x plus 5, we're going to multiply this by x plus 5. All right. Which would result, once you distribute everything out, x squared plus 3x minus 10. Okay. So what we're going to do now is these are now considered like denominators, and we've adjusted the numerators to compensate for it. So we're going to keep that the same. We're going to flip that to addition, and we're going to change this x squared, positive x squared, to negative x squared. Change that positive 3x to minus 3x, and we're going to change this negative 10 to positive 10. All right, now we're simply going to combine like terms. 2x squared minus x squared gets x squared. There's no other x but number. All right, so it's just minus 3x. There's no other constant, so it's plus 10. And then we write our new denominator that we came up with during the least common denominator process. And that is our answer for that expression. Okay, so as you work through these rational expressions, treat the process like you would a fraction. All right, if you have like denominators, simply just combine like terms, add the numerators. If they are unlike denominators, just multiply, all right, the denominators with one another to find the unlike, or to find the like, and then if whatever you do to the bottom, you do to the top. Okay. And then if you have any questions, don't hesitate to ask. Next time, we are going to begin solving these equations and trying to figure out, okay, what is that pesky little x actually equal to if we are ever presented any of these situations.